Hello everyone. The title of my talk is Over 100 GHz 3 dB down bandwidth by direct modulation of a coupled cavity DFB laser diode due to photon-photon resonance. The motivation of this work is to achieve stable single longitudinal mode operation and high-speed direct modulation in a single light source for optical fiber communication systems. In the following two slides, previous work for high-speed direct modulation will be reviewed. The first work is detuned loading in coupled cavity semiconductor lasers. Any dispersive loss mechanism is introduced. The lasing frequency is deliberately detuned from the loss peak. In the experiment, the resonance frequency has been doubled. The second work is photon-photon resonance. This effect relies on the carrier-sustained interaction between the lasing mode and its close longitudinal non-lasing mode. The present work relies on the lasing main mode and submodes in a coupled cavity semiconductor lasers. This slide shows rate equations for the photon density of the main mode, the photon density of the submode, and the carrier concentration. In these rate equations, betas are self-coupling coefficients and thetas are cross-coupling coefficients. In the present work, the lasing mode and submode are controlled by designing a coupled DFB cavity. The main mode is obtained by a quarter lambda shifted DFB. In order to obtain stable single longitudinal mode operation, the submodes are generated by coupled cavities. This figure shows a schematic structure of the proposed coupled cavity DFB laser diode. Region 1 has a quarter lambda shifted DFB. The phase shift delta omega 1 at the center of region 1 is -pi. Region 2 has uniform gratings. The region length L1 is 300 microns. The region length L2 is 310 microns, longer than L1 by 10 microns. The grating coupling coefficient kappa 1 is 40 inverse centimeters. Kappa 2 is 38 inverse centimeters, smaller than kappa 1 by 2 inverse centimeters. By controlling the grating pitch difference between lambda 1 and lambda 2, the main mode is mainly determined by region 1. The submodes are determined by the coupled cavity, which is composed of region 1 and region 2. This slide shows threshold gain as a function of delta L. Here, delta is the difference in the propagation constant beta of the laser light and the propagation constant beta 0, which is determined by the grating pitch. The parameter is the grating pitch difference delta lambda. When delta lambda is 0.1 nanometers, all modes are generated by the coupled cavity as shown in the left figure. When delta lambda is 1.7 nanometers, the submodes are generated by the coupled cavity, and the main mode is mainly determined by the Bragg wavelengths in region 1 as shown in the right figure. This slide shows the resonance frequency as a function of the grating pitch delta lambda when the injected current is 20 milliamps. The resonance frequency has a peak when the grating pitch difference delta lambda is 1.7 nanometers. This figure shows the resonance frequency as a function of the bias, which is injected current divided by threshold current minus 1. The resonance frequency is not a superlinear function of the bias, as opposed to the single cavity lasers. This slide exhibits frequency response when the relative bias is 2.5. The resonance frequency is 83.9 GHz. The 3 dB down bandwidth is 110.6 GHz. This slide shows oscillation spectrum. The wavelength of the main mode is shorter than the gain peak wavelength. The slight peaks of the several submodes exist. Finally, I would like to summarize my talk. Slightly asymmetric DFB cavity leads to the resonance frequency of 83.9 GHz. The 3 dB down bandwidth is 110.6 GHz. Both values are higher than the previous values. Thank you very much for your kind attention.